Hello everyone, and welcome to this second episode of the Shure Wireless Masterclass. This Masterclass is the virtual version of training that we have been running here and there in person, and this will prepare you for the exam on Audio Institute web portal. I let my colleague Marwan from marketing department, marketing manager, to introduce you and to give you some more details about the exam that you can take at the end of the 5 sessions. Marwan, please.
Hello, Andrea. Hello, all. As Andrea mentioned, we have the Shure Audio Institute. It's an online portal that we've created and has all the certifications and classes. So to access the portal, I'll share this link with you on the chat in a bit. But just to show you, once you reach here, for this region, it's Shure Miyasa, shure.talentlms.com. You just need to sign up. You have put your first name here, last name, email address, username, password, company, job function, and the country. And then once you sign up, you log in. I'll just do this quickly. Once you log in, you get the access to all the certifications and courses. So here I have already started the RF certification. If you click on this, I'll show you in a bit how to reach there. Once you click on this, this is what Andrea is currently giving, the module RF fundamentals that happened last week, and today is the analog of transmission. You can review this. Once you feel comfortable and ready, this is, you look for the Pro Audio Shure Masterclass Wireless Best Practices and Techniques exam. You click on it, and this will take you to the exam. How to look for certifications and courses. You click on certifications on top. So this is a list of certifications that are available. How to look for these. There are some ready. Just a second. On the right hand side, there is the course catalog, and in the course catalog you get all of these already there, but you can filter them by languages, by category, or general. So if you have any questions in signing up and in logging in, please get in touch with us or ask us in the next webinar. If there is anything you need, again, we are here to support you. Thank you, Andrea.
Let me get back in control of the screen. Here we are, hopefully. Okay. One more second for me. Oh, perfect. Now I'm on the right screen. And here we are. I just want to start with a funny episode that happened during the last lesson we did together. Some of you complained correctly that my microphone wasn't working fine. What I did after the session, I took my mic, recorded it. I blamed maybe the room, maybe the mic itself was having a problem, even if it's very unlikely, but you never know. It turned out that the problem was in my settings. But the first thing that comes to mind when something doesn't work, it's always the mic. So this is a very critical component in our audio chain, and this is why we really need to make sure that our microphone is working fine. Even more important, if this microphone is a wireless mic, because any kind of malfunction that can happen all over the chain, at the end the blame goes to the mic because it's the front end. It's something that everybody can see. This is why I think it's very important to understand as much as possible how a microphone, wireless microphones are working, and what we can do to improve the functionality and to make this RF connection more solid and stable. Today we go a little bit in depth on not too much, don't worry, but a little bit in depth about what happens for during our transmission, being it analog or digital. Exactly, we saw the importance and a little bit of history of wireless audio. We saw the RF fundamentals. So what are the waves that we are dealing with, electromagnetic waves, how big they are, and I may have a question for you. How many of you remember what is the wavelength of a 600 megahertz? You can answer in the chat. I'd be curious. And we saw the importance of the dimensions when we deal with RF waves. But today we see how we use these waves to transfer signals. This signal can be analog signals, specifically audio, but the same is applicable in example for video, or some of the same concepts can be applicable for video, or digital RF. And digital RF doesn't make a difference if you're transmitting and broadcasting audio or something else. Yes, guys. Okay, cool. Everybody remembers everything. Very good. So we'll see. We'll start from the analog type of signals, and then we'll move into the digital. So we need to transmit audio over RF, but the waves that we saw before are not carrying any information. So how do we make it happen? We need to modulate these signals in order to embed the audio signal or any other content that we need to transfer in this waves. So we have two different signals, two different waves. One is the modulating signal, and the other one is the carrier. When I see 478.750 megahertz on my wireless receiver or on my near monitor transmitter, that's the frequency of the carrier that is modulated by the audio. We have different ways to modulate the carrier, but that you can see on your screen. So we have our carrier, our baseband, and then if we need to carry analog signals, we mostly use amplitude modulation or frequency modulation. Phase modulation is not really used for an analog audio in any compartment. Amplitude modulation was the very first way that we had to transfer audio over RF. It's fairly simple to build, a transmitter and a receiver, and this is why it's been the first method, but it has some problems. One of them is the large transmission loss. So we need a lot of power, and we cannot go very, very far. A very limited bandwidth, meaning that we cannot have a 20 hertz, 20 kilohertz signal, but we are very much limited in terms of bandwidth. And from here, we have a typical radio kind of sound, no low frequencies, no high frequencies. And it's very susceptible to noise. So it's very easy for external noises to interfere with our signal. Even if it's not in use in professional audio, I'd like to show you this small animation that gives you an idea about how our signal is modulated. As you can see, the strength of a carrier varies depending on the modulating signal. This is what's making our system not so efficient, and in certain point, you can see that the amount of energy that we are transferring is absolutely limited. Therefore, we have an additional sensitivity to noise. We may decide to modulate the phase of a signal. I'm not really spending much time on it because we'll discuss it when we will talk about digital signal. But it's somehow a similar concept. We change the phase according to the modulating signal, but this is not really helpful when we need to send complicated signal like audio. It becomes helpful when we are transferring bits, 0 and 1. But in this case, it's not called phase modulation anymore. It will be called phase shift keying. And the most common way to transfer information using a ref is frequency modulation. The frequency of a carrier wave is varied in proportion to the modulating signal. With this method, we have obviously analog TV audio, we have radios, we have synthesizers, and all the professional wireless systems that are transferring analog signal. Here you can see in the animation that the major difference is that the strength of a signal is consistent. It doesn't depend on what we are broadcasting. Therefore, you can understand that is much less susceptible to noise because the strength of a signal, it's always there. It's interesting to see and to look at the same signal from another perspective. So if we look at a spectrum analyzer, what we see here is are two signals, analog signals. One is the pure carrier that's using a very limited amount of spectrum, and the other one is the same carrier modulated in frequency with a certain deviation. Deviation is what we were seeing in the previous slide as a difference in frequency. Here the frequency is on the x-axis, and we can see how the signal expands on the x-axis for our if we look at it in our analyzer, and we can see the amount of space that it's using. The amount of space that it's using is by law to be recognized by international rules as a wireless microphone. It cannot be more than 200 kilohertz. This has an impact on the capability of a system to transfer a full bandwidth audio signal, but still we are having much better performances, and we are much closer to the expected 20 hertz, 20 kilohertz audio than with AM. Later on, discussing the digital signal, after discussing the digital signal, we will see what are the limitations of the analog that are, as I said, are much less than in FM than AM, but what are the limitations of the analog systems versus the digital RF that is nowadays, I'd say, the new standard. So we have been kind of happily using the frequency modulation system for a while, but nowadays we have some benefits moving to digital. Before we look into it and we do comparison, I want to introduce you to the concepts related to digital RF transmission. So what are the basic combinations of audio and of digital and analog in a wireless system? We can have completely analog system, we can have hybrid systems, and we can have completely digital system. So we have a completely digital system in the moment where we have audio and radio signals that are digital. But we may have some hybrid devices. It comes to my mind the PSM 1000 in example, where we have control that is digital, signal processing that happens in the digital domain, but audio and radio signals broadcaster from transmitter to receivers are still in the analog domain. From now on, we will talk about purely digital system. Hybrid systems are still using frequency modulation, but purely digital systems are not. There are different methods in the digital domain as well. I'd like to highlight the fact that we don't talk about modulation anymore, but we talk about shift keying. Shift keying refers to discrete values of a binary signal, meaning we are transferring 0 and 1. And it's relevant only up to a certain point that we are transferring digital audio, or if we are transferring emails, or if we are transferring text, or whatever else we can move once it's been digitalized. So the first method is amplitude shift keying. Now imagine that this is a sequence of 0, 1, 0, 1, 0, 1. The modulated carrier signal will look as in the amplitude modulation, is modulated in amplitude, but we'll have two different levels, and the receiver will be capable of recognizing which of the two levels is sent. Other than that, we have frequency shift keying. Again, the same signal 0, 1, 0, 1, 0, 1, we have two different frequencies of a carrier. It cannot be too much the difference of the two different frequencies, otherwise we would be outside the deviation that can be functional for a wireless microphone. And then the third way is phase shift keying. 0, 1, 0, 1, 0, 1, we have positive, negative, positive, negative, positive, negative phase of a carrier signal. I need to say something. In this module, we are simplifying a little bit the things, but in this specific moment, what you are seeing, it has not much to do with what really is happening. This is an oversimplification, because if you do some mathematics, you will find out very easily that none of the three methods we have seen so far is capable of transferring enough bits per second to have an audio signal in it. So we will see more in details what's really happening, but I just want you to have an overview of these three methods, because this is helping us understanding one of the first benefits of a digital audio. RF noise does not affect digital audio. Now, if you know about digital systems, maybe, and if you are a little a little old like me, you may remember when the digitalization started to happen, that was looking like something without any problem. The digital, it works or it doesn't work. Then we have been learning that some issues can happen in the digital domain, and it's not granted that just because the signal is digital is not affected by noise at all. But it's not affected at all by RF noise, because the receiver will do an estimation trying to understand if the signal that has been eventually disturbed in the way was a 0 or a 1. Therefore, it's more simple for us to take the noise out of the equation, and we will have the same audio at the source and at the receiver. Of course, other problems can occur in the way, and we will see some of them shortly. Here are two different views of two different modulations. One is a 2FSK, so two frequencies shift keying. So the simplest possible frequency shift keying is using two frequencies, one for 0 and one for 1, and it will look like in the picture in a spectrum analyzer. It will look like the one you can see in the left of your screen. The 8-phase shift keying, or even a 2-phase shift keying, will look like block, exactly like the one you can see on the right of your screen. This may look like a digital TV channel, with the only difference that this is way more narrow. A digital TV channel is usually 4 megahertz, 6 megahertz, or 8 megahertz. This is much, much smaller, and it's, as usual, about 200 kilohertz. You can see that the span for the analyzer in these two pictures is about 1 megahertz. If you look at the two frequency shift keying, you will notice that it's using much more spectrum than the 200 kilohertz I'm referring to, but it's still used for wireless microphones. The only difference is that frequency shift keying, for several reasons, it's not used for UHF microphones. And it's used mostly for 2.4 gigahertz microphones, such as Shure GLXD, in example. And the rules in that portion of spectrum are a little different. So frequency shift keying, it's not used for UHF professional wireless microphones that are a little bit the scope of this training. So we won't go much deeper into this kind of modulation, while we'll investigate phase shift keying and amplitude shift keying more in details. Before we do so, I'd like to take you inside the box. Now, for who knows me, and for who doesn't know me, I can tell you straight away, I am not the kind of guy who loves to open a machine and know every single component inside. I like technology, but I'm very much a user and not a real engineer. I like to use the devices. This is why you don't get a schematic that is super complicated, but it's a bit simplified. But this is, in my opinion, the level of knowledge that we need to operate wireless systems consciously, knowing what's happening inside the box a little bit, without going too much in detail. So as you can see, we are having a transmitter in front of us. It can be any digital transmitter that has an audio input. It may come from a capsule, from a lavalier, it may come from a guitar, Doesn't matter. At this stage, it's an electric signal entering our preamplifier. And this preamp, most of the times, it's somehow an auto-gain preamp. If you notice, in the most recent digital transmitters from Shure, you don't have a real gain control. You have an overall gain, but you don't have a gain related to the preamplifier only. This is happening because the preamp can have different positions, maybe high, mid, low gain, depending on the input signal, in order to have the best conversion that is possible, to use the more bits, all the bits available in the transmitter. So together with the information related to the audio itself, we have to carry information about the setting of a preamplifier for every and each sample. So we have a preamplifier that is somehow working automatically, and then we have an analog to digital converter. Again, nothing mysterious. The converter transforms an electric signal into a data stream. Then we may have a DSP, digital signal processor. We may decide to do something to our sound, to transform it a little, to make it different for several reasons. And during the next session next week, we will go in detail about the processing that may happen in analog and digital domain. After this processing, we have another converter, because at this point we cannot send out 0 and 1 as they are. We need somehow to transform this 0 and 1 into another type of current, of energy, that will modulate our carrier. How is this happening? We have a small thing called PLL controller that is actually controlling a VCO, that is an oscillator producing the carrier. We are producing the carrier at this stage at one side, and we are modulating it with the signal coming from the audio path. After that, this will be sent to an amplifier, RF amplifier, that will broadcast the signal to an antenna. I hope it's simple enough and it's clear. If not, as usual, you can ask your questions, and I'll be happy to answer them if they are not too difficult. On the other side, we have the receiver. Again, if you open an Axion digital receiver, it's probably a little more complicated than this, but here we have all the relevant blocks that help us understanding the things that we can somehow control. So the first thing that we see after the receiving antenna is the front-end filter. The front-end filter is like a bandpass filter for a ref. So it's not working in the analog domain, but it's working it's not working in the audio domain, but it's working in a ref domain. And it's used to cut out all the frequencies that we are not interested in. We have two types of front-end filter, fixed and track tuning, meaning that we may have a filter that moves according to the frequency that we are using to tune our receiver, or we may have filter that is fixed. when I say bandpass filter, or when we look at the picture, the front-end filter may look very narrow, with the steep angles, but it's not how it is in reality. It's like a very soft low and high shelving, and it's not cutting out the things completely. When we will move into frequency coordination, and if you are familiar with wireless workbench, the front-end filter is one of the most important parameters to understand how a microphone system can be coordinated. Because whatever is outside of our front-end filter doesn't bother us. So we can have, let's say, almost every kind of interference or other source. As long as it's outside of the limits of our front-end filter, we may ignore it. After that, we have an oscillator controlled again by a PLL. And this one goes into a mixer. As in the audio, it's just a 2-channel mixer. We are shifting down the frequencies in order to have a signal that we can handle better. Handling signal at 600, 500 megahertz in the UHF domain, it's not that easy. And handling frequencies that can be tuned and can change, it's even more complicated. So for engineers, it's easy to make this demodulation part in 2 steps. We bring down the signal to an intermediate frequency that's typically 10.7 megahertz with another filter, intermediate frequency filter. So we clean the signal a little more, and then we are ready to go into another amplifier, get the signal to the level we need. So it doesn't matter if my microphone is 80 meters away from the antennas and I receive it at minus 85, minus 80 dBm, or it's very close to the antenna and it's super loud. After the intermediate frequency step, all the chain will perceive the signal in a very consistent way. But at this point, what we are dealing with, it's still an electric signal that has to be converted into an audio stream. So in data, at the data level again, 0 and 1 again, we may have another DSP part that stands for Digital Signal Processor, and then we have digital audio. At this point, we can go out if we have, an example, a Dante port, or if we have a ES3 port, we can go directly out with our data stream. If we have an XLR or a TRS analog audio output, then we have an additional converter. And after that, we can go to kind of amplifier that leads to the audio output. Okay, I hope this part was clear enough. Again, if you have questions, please feel free to ask them. And we can go back and talk a little bit about our bit rate. So if we look at the different typical signals that we deal with in audio, 24-bit, 48 kilohertz will require a lot of bits per second. That in bit rate is 1.252 megabit per second. And this is somehow the standard for wireless microphones. A few more words on this. Someone thinks, oh, why we don't have 96 kilohertz? we all know that the sample rate is related to the highest frequency that we can convert. So having filters working at 24 kilohertz for a single signal, as it is a microphone, or even for a mix, as it eventually may be a complex signal program. But on a single microphone, on a single signal, we don't see major benefits of working at highest sample rate. And when we are talking about RF transmission, any increase in the sample rate will carry a lot of additional problems in terms of reliability. So this is why, to have a good balance between audio quality and reliability, stability of a signal, Shure decided to have inside digital wireless microphones converters operating at 24-bit 48 kilohertz. So, but 96 kilohertz will just be double the data. Now, if we go back and we think about our modulation schemes, the simplest we saw is only having two states, 0 and 1. Now, the amount of information that we can carry having only two states, it's very limited. Now, if we can carry more states, in example, we are having a 2-bit transmission, we can carry 4 states at the same moment, then we are already doing something, carrying more information more easily. We can have more bits, we can have more states. Now, if we relate this information to symbol coding, without going in the mathematics of calculating how many bits a 4 PSK is really transferring, oops, something popped up on my screen. Okay. Capable of having this. Nothing. Before I spend off of a presentation trying to remove the bar, sorry, please understand. And you can see the application that I have on my laptop right now. Symbol coding. The more symbols we can transfer within a single cycle, the more efficient our system is. So if we can transfer, we have only two frequency states, positive, loud and, how to say, more frequency or less frequency, then we can transfer 1 bit per time. With the 4 PSK, that is phase shift keying, we can transfer 2 bits at a time. With 8 PSK, we have 3 bits at a time. To transfer 4 bits at the time, we start working with QAM or Quadrature Amplitude Modulation. I said I don't want to do the calculation about the bits that every one of these modulation schemes carry per second. The reason is that whenever we transfer a digital audio signal, we don't just have this raw digital audio, we have a lot of additional information that are required in the digital world to keep the clock on track, to have a syncing, let's say, between the transmitter and the receiver. Therefore, for a 24-bit and 48 kilohertz, we don't just add the raw data, but most likely every single digital word will be 32 or more bits in reality. So let's see how we can transfer more data. This is a two-phase shift gain. So I can invert the phase 180 degrees of one cycle versus the other cycle of a carrier. And here I go. I have 1 bit per symbol. But if I'm capable of using also the 90 degrees and the 270 degrees, I can carry 2 bits every hertz, every cycle, every time I have a full cycle on the carrier. And this is double the data. If I have the capability to use 8-position phase shift gain, even better, I can carry 3 bits each symbol. This is relatively already a good standard. Now, of course, on paper, it's very easy to say, okay, why we don't have a 48 PSK? The answer is fairly simple, because the engineers who are developing the products at Shure, they would say, yeah, build it yourself, because there are technical limitations with what we can really do. So if we don't want to put our receiver too much under stress, and we don't want our system to work only in perfect conditions whenever there is no noise and everything is super perfect, that is not where we run shows and events, we can't go more than this. But we can still have more symbols, more bits per symbol than 8 PSK. The answer is QAM. QAM is not using only the phase shift keying, but it's integrating the amplitude shift keying too. So here you can see that every symbol, so every hertz, will represent 4 bits. Here we are carrying additional information and without giving too much headache to our receiver, because on the amplitude shift keying we have 3 positions, and on the phase shift keying we have 4 positions. So it's we have 8 positions. So it's reasonably simple to build something like that. Now, for who's more interested in details, I can say that, again, I'm simplifying things. In example, X in Digital is using a kind of 16 QAM symbol coding, but it's not exactly like that. Most of manufacturers decided to use specific modulation schemes that fit the specific needs of their system. And then there are other details that are usually proprietary information, so information that are not disclosed, not even to me, about exactly where the bits are located. And but from a user point of view, we don't really worry about it. What we need to know is that the system is using a mix of amplitude and phase shift keying. Can we prove it? Yes. And I'll tell you how to prove it in the hard way. If you have, I think most of you is at home, so you may not have a really handy PSM receiver and an X in Digital transmitter. But if you have so, you can listen to your PSM receiver, and if you put the 2 antennas, transmitters and receivers, very close, you will notice that the noise squelch of a PSM will shut down when the 2 antennas are extremely close. Another proof of it is that in case you have a very old vintage guitar with a digital transmitter too close to the pickups that are not shielded, you may hear some noise coming through the guitar. solution, in case you ever encounter this problem, is very simple. It's just keep some social distancing between the transmitter and the receiver, or the transmitter and the guitar. If you are having a body pack mounted on a guitar strap, few centimeters up on the strap will solve the problem. Except if your guitar has really some other problem and it's acting like an antenna, in that case you probably want to look at the shielding of a guitar. So we have a solid system to operate. What can go wrong? This can go wrong. What I'm showing you now is the view from a receiver perspective of signals that are not perfectly hitting their target, or for some reason the receiver is not looking at them like they are perfectly hitting the target. When is this happening? In two cases, when the carrier to noise ratio is not good, or when the gain of a transmitter or of a receiver, the RF gain is not correct. In this case, for the receiver, it's not easy to discriminate where each symbol is hitting, and therefore it's more difficult to understand the signal that is receiving. This will increase the bit error rate. What is bit error rate? Is simply the number of data errors over time. You can see an example here. And how we call it. So if we miss 3 bits out of 10, our bit error rate is 0.3. The moment where our bit error rate is 1, it means we are not getting anything. Okay? And when bit errors occur and when this bit error rate increases, when we have too much gain in the system, when the noise is too high, when we suffer from multipath interference, when we don't have enough RF, or when the circuits are not linear and there is distortion happening. We'll see more in details what the squelch is, but for who's already aware or for who's not, we can say that the squelch is a gate externally controlled by something else that opens or closes the audio output. If we don't satisfy the criteria of the squelch, this will close. If we have bit error rate that is too high, then our squelch won't open and we will have silence out of our wireless microphone. If you think correctly about a ref, we can say that sending audio over radio frequencies, it's all about signal to noise ratio. I usually stress a lot on this point. We have a noise floor usually, and we need to be louder than this. We need to seed the noise to be recognized as a transmitter by a receiver. How is this affecting our systems? You can see with absolutely random values the difference between digital and analog. So if our signal to noise ratio, or we can call it, it's called in other parts of the world, link margin. If we are 28 dB louder than the noise floor, both digital and analog are sending flawless audio and everyone is happy. If this signal-to-noise ratio reduces, in the analog domain, we lose little portions of signal. Now, is this having immediately an impact on the quality of the audio that we are receiving? The answer is no, not immediately. Because in this scale, if we think about 25, 23, 22, and we are having a professional wireless system, being it analog or digital, doesn't matter. There are ways to preserve the integrity of the analog signal as well. But at some point, when the signal-to-noise ratio degrades, we'll lose portion of the signals in the analog domain, while digital will still be consistent. At some point, the analog receiver will receive more noise than usable signal, and squelch will kick in, muting the analog microphone. At this stage, most likely our digital microphone will still be capable of operating, will still have enough data to process to keep the signal flowing. At some point, we'll start degrading very quickly and will cut off, usually at a lower signal-to-noise ratio. Now, if you look at this schematic, please be aware that the numbers are related to two specific systems. Probably the digital system may be ULXD type of system, and in the analog domain we have a pretty good system. It's working with 10 to 12, 13, 14 dB of signal-to-noise ratio. An entry-level system will need maybe more better signal-to-noise ratio to keep operating. On the digital domain, Axion Digital can still broadcast and receive signal with 7, 6 dB of signal-to-noise ratio. So it's very much dependent on the system where these numbers are allocated. I see some questions in the chat. Thank you for the questions. I'll get to them. Just a little note, I didn't remind you. You have a Q&A section. So if you can kindly post your questions there, is helpful. But otherwise, I will try to answer the questions that you asked in the chat as well. A few more things. Data compression and codec. This is a simple concept. Whenever we build a digital word out of some raw digital audio signal, we use a codec. How do we package the information? Is the codec. Some codec are totally uncompressed. We can think about AFF or WAVE or other billion codecs. Some of them are lossy, meaning some data is not there. And you can see the two pictures. The lossy compression will not give back the same quality of a lossless compression. But lossy compression can be helpful when you need to transfer data. An example, at least in the old times of internet, when the connection wasn't as fast as it is today, MP3 were heavily compressed, but this was the only way to transfer data over internet. Nowadays, we can use lossless codec. The same is applicable into digital audio for wireless microphones. We use codec. We use a form of compression, but all the different manufacturers built lossless codec. exactly like your Waves or your IFF or whatever format you use in your Pro Tools sessions to record, in order to keep the quality. You don't want to spend $2,000 on a microphone and then get an MP3 output, of course. So it's important to understand what the codec is and how it's used in this specific application. One of the benefits of digital is the capability of encrypt the signal. I will tell you the truth. With the limited knowledge I have about the audio signals, if I had to steal something, probably stealing at the RF level with a digital signal would be my very last option. If I had to steal something, I would rather try to connect a USB stick in a mixer. That said, most governmental institutions or private institutions require that the signal that goes through RF is encrypted. The most used protocol encryption protocol is AES 256 or 128. That is a computational system that has no known weakness. It takes too much time to be decoded, and the encryption happens with a key that is exchanged when we sync the transmitter to the receiver, and only these two entities know this key. That is the key you need to get audio out of the RF signal that you receive. If you are not specifically requested to enable encryption, I do not recommend to enable encryption on your digital wireless microphone, because doing so, what you do is to increase the latency. And before we get to an end, I think it's very important to spend a few words on latency. Latency is not only the very reason why we had digital wireless systems 20 years after digital mixer. Latency is the time delay from input to output. And in our industry, in our events, in our shows, this is created by a mix of factors. But every digital signal processing, every digital device in your chain needs time to be operated. Therefore, if we have multiple digital devices, we increase our latency. And we may increase our latency to a level that we can start hearing it and it can start to be disturbing. Here we have a value of 5 milliseconds that ideally here we have a value of 5 milliseconds as a limit of disturbing. Below 5 milliseconds, most of the time, our brain is capable of combining the original signal and the signal with latency in one. Between 3 and 5 milliseconds, very trained ears, like sound engineers, but like musicians as well, may start noticing it, but without any disturb, with few exceptions. When we notice latency, when we are capable of comparing the two sources, so when we have an original signal that comes at time 0 and a signal with latency that comes after a while. So if you are a vocalist or a violin player or whatever, and you have your instrument or your voice, and then you have in-ear monitors, you can notice and start to be disturbed with values of latency of the overall chain around 5, 6, 7 milliseconds. The same concept is not exactly applicable with monitors that are maybe 1, 2, 3 meters away. Why this? Because the brain is somehow managing, thanks to the information that can get from the eyes. So you look at the monitor, you know that the monitor is there, and your brain is somehow predicting this latency. But when the source is straight into your ears, this is not happening. Over 5-10 milliseconds, it starts to be very disturbing for any musical and even some speech applications. So if you're trying to speak on a PA with a microphone with 20 milliseconds of latency, something you can easily try on your digital mixer with even with a simple SM58 connected to it, and you start adding latency to your channel, you will find out for yourself what is the maximum latency level that you can tolerate. So latency has been delaying a lot the digital wireless, because it took time to reduce this latency. And the more the technology progresses, the more this value goes down. So if you think about, I don't know if you remember or if you ever used it, the very first 01V mixer by Yamaha was having all by itself 4 milliseconds of latency. Now almost every digital mixer is in the range between 0. Something milliseconds and 2 point something milliseconds. And a big portion of this latency is introduced by the plugins. So if you have a mixer straightforward without any external processing device, you are most likely be around the milliseconds or somewhere there, depending on the mixer, obviously. Every mixer and every... It's been delayed a lot. But why manufacturers have been looking so badly for digital wireless? We're not disturbed by noise. Yes, this is one point. But the other one is that we can see from the next two pictures, that they are much more efficient. If I look at this slide, I may think, no, it's somehow the same. And yes, it is the same the moment all the transmitters are more than 2 meters apart. But the moment all the transmitters are very close to each other, what we see is that the analog systems are producing a lot of harmonics and spurious frequencies that will increase the noise floor, while the digital transmitters have a much cleaner transmission. They produce much less intermodulation distortion. We'll see more in details what is intermodulation, how it occurs, and how we can deal with it. How to make a system that is efficient and can use less spectrum or can put more channels in less spectrum. We have 3 criteria to match. Linearity of the RF amplifier, and definitely transferring 0 and 1 instead of complex audio signals gives us the opportunity to work with more linear RF amplifiers. Selectivity of filters, because of course, the more we can ignore other sources of problems, the better our system will perform. And one of the last things that we added is the capability to work on to program frequencies on an equidistant grid. Now, if we are talking about analog systems and we try to put them one on 600 megahertz, the next one on 601, and the third one on 602, already with 3 microphones, I may start experiencing intermodulation. As I said, we'll look at intermodulation more in detail. With digital systems, we don't have this issue. We can put them on a grid that's like, let's say, every 400 kilohertz, every 300 kilohertz, not because they do not produce intermodulation, but because their intermodulation products are not strong enough to disturb us. Plus, some systems provide you with an additional feature that is called high-density mode. High-density mode is a special mode of transmissions that at Shure means we reduce the power, the emitted power, and we reduce the deviation of each signal from 200 kilohertz to 125 kilohertz in order to achieve the result of having many more channels in the same space. Let's say that the density we can reach with a normal analog system is with a good analog system is about 4 transmitters per TV channel. Digital radio microphones can have a density up to 20 plus per TV channel, meaning in 8 megahertz I can have 20 plus microphones. In high density mode, we can have up to 60 channels in one TV channel. That means even with the shrinking of a spectrum, even with difficult RF conditions, with high density mode, we are really capable of having a lot of microphones on air without producing too much noise increase. What we pay to get it is that the coverage area, it's obviously slightly reduced compared to normal mode. But usually if I have so many channels, I don't have to cover big areas with all these channels. So it's a trade that has some value. Now I realize that the 1 hour of this training is already very much gone. So very briefly, some conclusions. What are the advantages in digital systems? Wider and flatter frequency response, and we'll find out better why during the next session when we will talk about processing and we will talk more about the audio. Same, we can have a more extended dynamic range because we don't have companion system. But most important, we can have more systems on air at the same time. We can have HD mode. We can have reduction of intermodulation products. We can have a better resistance to multipath and interferences. And we can have encryption for whoever needs it. So I hope it was clear. In the next session, we will talk about the audio side, the audio consequences of what we have been discussing so far. So we'll go more in details about why digital audio has a wider and flatter frequency response, why we don't have audio artifacts, and why the dynamic range is better, and eventually the signal to noise ratio at an audio level is better. Okay.
All right, Andrea, thank you very much. We will take now 5 to 10 minutes to answer any questions. So the first question from Ranjan. In Wireless Workbench, the front-end filter parameter refers to the filter type for each receiver channel, while the filter selectivity parameters below in megahertz refers to the front end of the device.
So thank you, Ranjan, for your question. And so the front end filter parameter refers to the filter type. Let me open Wireless Workbench so I can exactly show what I'm referring to. Just give me a second. I think you are talking about the filter settings into the profile of the devices. Now, just a second that I open the software, so it's clear for everyone. We are talking about the criteria of coordination. And correct me if I'm wrong, you are referring to this part of the settings. So the front end filter is here, and it has its own setting, while the second portion is the channel spacing. So the distance from carrier to carrier, how much space it needs to survive. We'll look at this again in more details when we will discuss frequency coordination basics in shortly. It's in 2 weeks from now. I see some more questions.
Yes, again, a question from Ranjan. We know that AM is highly susceptible to RF interference. How does using AM in 16 cam UAM overcome that to prevent bit errors?
Very good question. First of all, it's not using amplitude modulation, but it's amplitude shift keying. And it doesn't. Technically, like it's acceptable not to RF interference, while it's acceptable to noise. But being a digital device, we found out that the noise by itself is not disturbing us, because as long as the system is engineered correctly, we are still capable of recognizing the bit that we are transmitting. I see that there is another question always related to it. Why 16 QAM devices need a higher CNR than 8 PSK devices? There is no, no, the answer is no. 16 QAM devices, for several industrial reasons and the way they are built, are usually requiring or are capable of operating in a harsher condition than 8 PSK devices. But that would require an indirect engineer degree that I don't have. And from a user perspective, what we are interested in is to know that 16 QAM, depending on how it's engineered, if it's engineered properly, and I'm talking about Axon Digital in this case, that again is not using a pure 16 QAM modulation scheme, doesn't require a higher CNR than 8 PSK device that in real life is ULXD. By the way, there is a very simple way to recognize it. Most likely, the top tier system, the one that costs more, works with a worse signal-to-noise ratio than the systems that are mid-tier. But this is not only related to the modulation scheme. When we talk about real devices, it's always a mix of a modulation scheme, but also the components, the tolerance of the different components. So without taking the discussion into the engineering field, this, as I said in the beginning, it's simplifying a little bit the concepts, because the real devices are always made with many more choices than the one I presented you. But the scope of this training is to have you confidently using wireless microphones. I'm not the guy who can teach you how to build wireless microphones, and I wouldn't do, because you would become a competitor maybe. I'm kidding, obviously. I see that you are, oops. Oh, front-end filter is in megahertz for each channel. Yes, but front-end filter doesn't mean that we cannot have anything inside the front-end filter. It just means that we don't care at all about what is outside the limit of a front-end filter. By the way, we'll discuss more in details this topic during the frequency coordination. Is there any other question? Marwan?
I think that's it. We don't have any more questions.
Okay, so as usual, you will get an email with a form. Please feel free to submit if you have additional questions, you can ask them there. Any feedback is welcome. And I guess I'll see you next week. Or better, you will hear me next week for the third episode. That will be about signal processing, and we'll talk shortly about the specific of in-ear monitors, transmitters, and receivers.
And Andrea, do you want also to mention the Shure and Odinate webinar happening next week?
Oh, yes, I want to mention it. Based on one of the questions we received, we decided to have a quick and open chat with Augusto Marcondes from Odinate. It will be, I think that in these days we all had a lot of webinars, a lot of occasions to learn how to do things. So we thought that it might be interesting to know a little bit about why to do things, so why audio networking, and some hints about history of audio networking. So it won't be a Dante training, it will be more an open discussion about Dante, and it will happen next Monday, 3 p.m. Dubai time, and you can register. I think we are promoting it on many different channels, so maybe Marwan can help you understanding how to register better than me. From my side, that's all. Thank you very much, and I hope to see you next week.